So dear students, today we will finish off our topic on active and passive filter. In the last class, we had started our introduction on M-derived filter. First, we will finish our discussion on M-derived filter, and then we will discuss about the new topic, that is active filter, and we will try to finish off that topic also. So let us now continue. So I'll hurriedly revise what we discussed in M-derived filter in the previous class. So first is the main disadvantage for constant K filter was that the attenuation characteristics were not desirable. Desirable in the sense that uh, the attenuation was not rapid or sharp beyond cutoff frequencies. So that's why we went for M-derived filter, and in M-derived filter we could introduce rapid attenuation. And as we discussed, rapid attenuation is very important. We must have sharp cutoff characteristics, sharp cutoff frequency, so that only the desirable frequencies are passed through the given filter. However, in case of M-derived filter, the characteristic impedance behavior remains same. Only in terms of attenuation we get the desired characteristics. Then we had seen that how do we obtain M-derived filter from the prototype filter. And I told you that in case of T section, the series arm of prototype filter is multiplied by a constant M. And in pi section, the shunt arm of the prototype filter is divided by constant M. And this M is a real value, having value lying in the range from 0 to 1. Okay, and this M has been introduced in the circuit in such a way that your characteristic impedance of your original prototype filter and the M-derived filter, that remains same. We had seen its analysis in the previous class as well. So this is what we saw in the previous class. Here we have mentioned about your characteristic impedance of the original T section of the filter, and this is the characteristic impedance of the M-derived T filter section. And I told you that we have to assume that both characteristic impedances are same, and by implementing this expression we get the new, you can say, shunt impedance for your T section, which has factor M included in it. So we had seen its derivation in the previous class, and this is how we represent M-derived T section. Then we have M-derived pi section. So for pi section, as I told you, your shunt arms, they will be divided by M, and for this we have to obtain the value of Z1, new value of Z1, that is Z1 dash. So again we will carry out the same thing. We will equate the two characteristic impedance, the original one and the modified one. So if we make them equal, we can find out the value of Z1 dash, that is new value of series impedance in your M-derived pi section. Okay, so this is what we had discussed in the previous class. Fine. So then further in M-derived pi section, we have obtained the expressions by making characteristic impedance equal. Now, so in today class, we start with the analysis of M-derived low-pass filter. So in the previous slide, we have just talked about M-derived T section and M-derived pi section, but we now need to look into how does low-pass filter and high-pass filter in the case of M-derived sections behave. And we have already seen in the concept of filter that your shunt arm of T section and the series arm of pi section, that will be in resonance. Okay, so if you see here, I'm showing here T section. So in T section, if you see, we have L and C in series in the shunt arm. So this will be in resonance. Whereas in pi section, will have L and C in parallel in the series arm of the pi section. Okay, and we will assume these arms to be in resonance, and we know that during resonance we have the impedance, minimum impedance, then it behaves like a short circuit. Okay, and if we have maximum impedance, that means we have open circuit. So we will have in case of resonance, short circuit for the T section and open circuit for the pi section. Okay, so you see here in the T section, if we have short here, so we'll have such kind of thing. Say, I told you earlier also, if we have short here, so whatever input you provide here, output will always be zero because we have a short. Okay, so that means your input has been provided infinite attenuation. Okay, and whereas in case of your pi section, your series arm will be having open circuit. So if you have open circuit, so whatever you have the at the input, it cannot go out at the output. So this gives us infinite attenuation. So what does it mean? That we will have infinite attenuation in the T section as well as the pi section. Okay, and the frequency at which we get infinite attenuation, we designate that frequency as, you can say, resonant frequency and omega infinity or f infinity. So till now we have talked about the cutoff frequency. Now we come across one more frequency that is known as infinite frequency, and that is represent, or you can say resonance frequency, that is represented as omega infinity. Okay, so what we do here, as I told you, this omega infinity is nothing but the frequency at resonance phenomena. Okay, so in T section, this shunt arm has two you can say component L and C in series and in resonance. And we know that during resonance, what happens? During resonance, we have this expression omega square is equal to 1 by LC. Okay, omega square equal to 1 by LC. Okay, so so if you use this omega square equal to LC here, so what we have, this is the L in case of M-derived filter. This is what we have got here. This is L. And what is C here? MC. So we have MC. So this is nothing but the same thing, omega square equal to LC. I have substituted the value of L and C for the shunt arm in case of M-derived filter. And if you solve this, you get omega infinity square is equal to 4 by LC into 1 minus M square. Okay, and if you remember, we had derived the cutoff frequency for the prototype low pass filter. Okay, this is what we had obtained in previous classes. So same is the case here. So we have omega c square equal to 4 by LC as cutoff frequency of the prototype low pass filter, and we have this frequency as the infinite frequency or the resonance frequency of the you can say M-derived low pass filter. Okay, so we will obtain their ratio, that is we will divide the 2 omega infinity square by omega c square, and we get 1 by 1 minus M square. And we express omega infinity or the resonant frequency in terms of cutoff frequency. You get omega infinity equal to omega c by under the root 1 minus M square. And you can substitute f infinity and fc in place of omega infinity and omega c, and we get finally this expression. And now what we have done, we have obtained M, that is the value that we have introduced in M derived filter in the form of fc and your f infinity. Okay, so this is how we analyze M derived low pass filter. Okay, we have obtained the value of M in terms of cutoff frequency and resonant frequency in case of your M derived low pass filter. Fine. So now let us move forward. So now we look to analysis of M-derived low pass filter in case of pi section. Okay, so same kind of analysis will apply here. All that has happened here is instead of T section, now we are discussing pi section. Okay, so for pi section we have already obtained the value of this C and L. So this is the value of C in the series arm, and this is the value of L in the series arm of pi section. Okay, so here this series arm, it will be in the resonance. Okay, so in the pi section we will have series arm of the pi section will be in resonance. Okay, so and remember one thing, like if you again apply that resonant formula to these two values, you will get the same resonant frequency. Okay, so the frequency of resonance for pi section will be of the same value as we have obtained in the previous slide. So that will give us omega infinity equal to omega c upon 1 minus m square under the root. Okay, so this is how we analyze M derived low pass filter in case of pi section, and this final result for M is also same. Next, so now we discuss M derived high pass filter. Okay, and for high pass filter as well, we will analyze both the sections, T section and your pi section. So I think you are able to recall, this is your M derived high pass filter. Fine. So in case of high pass filter, in the series arm we have capacitor. Okay, whereas in case of low pass filter T section we had inductors here. Okay, so again same kind of thing will apply. This is our shunt arm, and in the shunt arm we have L and C in series. Okay, and this shunt arm of T section, it will be in resonance. Okay, and it will provide short circuit to the input. The same kind of analysis as we have seen in the low pass filter. So under resonance, what we will have, we will have Xc equal to XL. That is this is our Xc and this is XL. So what is our Xc? Xc is 1 by omega c. Okay, so this is what we have. This is the value of C, and omega is, we have omega infinity. So 1 by 4m by 1 minus m square into C. This is the value of C into omega infinity. I hope you know that Xc is nothing but 1 by omega C. So this is what we have substituted here. And what is XL? XL is your omega L. So omega is omega infinity, and what is L? L is L by m in case of M-derived filter. So this is what we get here. And if you solve this expression for omega infinity, you get under the root 1 minus m square divided by 2 under root LC. So then we substitute 2 pi f naught for omega naught, sorry, omega infinity, and we get f infinity like this. Okay, then as we did in the low pass filter, we have already obtained the cutoff frequency for high pass filter, prototype high pass filter. This we did in constant K filter, and this was the cutoff frequency. So if you substitute this value of cutoff frequency here, okay, see Fc equal to 1 by 4 pi under root LC. So here this is 1 by 4 pi under root LC. So if you substitute Fc in place of this, we get this. So we get F infinity equal to under the root 1 minus m square into Fc. And from here, we obtained the value of m in the same way as we had obtained. And this value of m is different from what we had obtained in the low pass filter. Okay, but analysis is quite straightforward. And what we are doing, we are basically trying to obtain the value of m for given resonant frequency and for given cutoff frequency. So in the numerical or while designing M-derived filter, you will be given two values, resonant frequencies and cutoff frequencies. For that, you will obtain the value of m. After obtaining m, you will apply the concept of conversion of prototype filter into M-derived filter. Okay, you will represent M-derived filter by using m, and then you will substitute the values of m in the design equations that we have seen. Okay, so now let us move forward. So this is for your high pass filter pi section. So in case of pi section, we will take into consideration the series arm. Okay, so this will be in the resonance, as we have seen that inductive reactance and capacitive reactance, they must be equal. Okay, so what do we have? We have this is our omega L, that is inductive reactance. See, what is our L? 4m by 1 minus m square into L and into omega, then equal to xc, that is 1 by omega c. So what is our omega c? So you see here, this is written as mz1. Okay, so mz1, and what is z1? Z1 is your 1 by omega c. So we have 1 by omega naught c by omega infinity c by m. Okay, so we have xl equal to xc. This is our xc. Okay, so the value of c here, the value of c here is actually, you can say c dash is nothing but it is c by m. Okay, so if you substitute, you get this, and if you solve it, we get this as omega infinity, and we get f infinity. Okay, and if you substitute the value of fc here, you get this one. So again, that this expression for pi section of high pass filter is also same. So you can say that whether it is low pass filter or high pass filter, in case of T section and pi section, the resonant frequency expression is same for both the sections of a corresponding filter. Okay, I hope this thing is clear to each and everyone. So this is our numerical example. This is very straightforward. Now you see here that we have to design M-derived low pass filter, both T and pi section. And what we are given? We are given design resistance, that is R0. We are given cutoff frequency, that is FC. And we are giving infinite attenuation frequency, that is F infinity. So as we have seen, first we will try to find out the value of M for given fc and f infinity. So from this we have obtained the value of m, that is 0.661, and you can see here the value of m lies between 0 and 1. Okay, so our first job in case of m derived filter derivation or designing is to obtain the value of m, and then after that we will use the design equations that we had discussed for prototype filters. Okay, the value of L, the value of C, and then we will use the structure of the M derived filter by using the value of M and L. Let us see. So for prototype low pass filter having cutoff frequency FC and R naught equal to 500 ohm, the series inductance, series arm inductance, this one, we had L here in the prototype low pass filter. So that L, or you can say L1, was equal to R naught by pi FC. So this is our L1. Okay. Then we had C in the shunt arm. Okay. So for that, the formula was C equal to 1 by pi R naught FC, and this is our C. Okay. So we have obtained M, we have obtained L, we have obtained C. Now we have to obtain these values. Okay, we have to obtain mz1 by 2. We have to obtain z2 by m. 1 minus m square by 4m into z1. And what was our z1? Z1 was nothing but inductor in the original prototype filter. Z1 was nothing but it was equal to L1. So what does it become? mz1 by 2, ml by 2. So this is ml by 2. We have to obtain the value of ml by 2. This is ml by 2. Okay, and these z2 dash, this we have seen in the derivation of our prototype m derived prototype filter. So then we have ml by 2, then we have mc for capacitor, it is MC, we obtain the value of MC like this. Okay, we are taking into consideration T section first. Okay, so after we substitute these values, we are able to design the T section of M derived low pass filter. Okay, so if we move forward, so now we have to look for this shunt arm. Okay, for shunt arm, what we have 1 minus m square by 4m into z1, and what was z1? Z1 is L, so we have to obtain this value. So if you substitute all the values, this is what do you get? This is nothing but this one. Okay, so we have basically derived our T section, M derived T section low pass filter like this. Now for pi section, we will have a term MC by 2. Okay, so you substitute value of M, then C, and you get this. Okay, similarly, we need a term ML. You see, this is our pi section. For pi section, we have MZ1. MZ1 is nothing but ML. This is ML what we have done. We have 4M by 1 minus M square into Z2. Okay, so you have to reverse this, because in capacitor we have the reverse thing. So we have 1 minus M square by 4M into C. This is nothing but this value. So we get this as 0.090 microfarad. Okay, and this MC by 2 value will come here. So this is 2 by M, this will become M by 2 into C. So this is how we are able to design M derived low pass filter T section and your pi section. Okay, so students, before I move to active filter, let me ask your doubts related to M derived filter, if any. So students, after we have completed the discussion of M derived filter, now we move to new topic, that is active filter. And active filter is very important topic, and you need to understand the concept of active filter. So active filters are those filters which are designed using active components, and one of the active components is your operational amplifier, that is op-amp. And I hope all of you know the basic concept of operational amplifier. This operational amplifier is available in the form of integrated circuit IC 741, and you must have seen its working in your introductory classes of analog electronics. Okay, active filters are designed using operational amplifiers. So if we look into the advantages of active filters, uh, the first important advantage is that in case of active filters, we will not have inductors. And let me tell you, these inductors are very bulky in nature, and your circuit becomes very large if you have inductors in your electronic circuits. So if you use active filters, we will be dispensing with the bulky inductors, and in active filters we have only resistors, capacitors, and op-amp, because of which we will have cost saving, we will have compact design, and the losses in the circuit will also be very less. Okay, another thing is, because of the use of operational amplifier, we will also have high gain and desirable impedance characteristic in case of active filter. Desirable impedance characteristic means we will have high input impedance and low output impedance. Okay, and because of the availability of operational amplifier in the form of IC, your active filters, they are compatible with your integrated circuits. And just for your you can say knowledge sake, I have included a figure on the left hand side. You can see here that this is your operational amplifier. Okay, so your operational amplifier has two terminals. One is indicated positive and another is indicated negative. Positive terminal is called non-inverting terminal and negative is called inverting terminal. And this is how we represent operational amplifier. Okay, and we have one terminal that is called as output terminal. Okay. Still we cannot say that active filters do not have any limitations. There are certain issues or limitations of active filters as well. We cannot have any filter which is perfect in all the sense. So in case of active filters, the selectivity and the cutoff frequency FC, these are the function of gain. Okay, so they become gain dependent. So as the gain varies, your cutoff frequency and selectivity of the filter changes. Okay. Another thing is, your active filters are not very stable. So there is a tendency with the active filters getting unstable because of, you can say, large amount of gain your operational amplifier provides. So these two issues we must look into, and we must also be aware of while working with your active filters. Next. So I hope you remember the concept of transfer function that we had discussed in our previous classes in detail. And we know that your transfer function was the ratio of output in frequency domain to the input in frequency domain. And in fact, we had complete unit on transfer function. We also did numerical to obtain the transfer function. And while calculating transfer function, we had taken the help of Laplace transforms also. We expressed our outputs and inputs in the form of Laplace domain, and then we obtained the transfer function of a given circuit. So in case of active filters, again we will discuss the working of active filter in the you can say form of transfer function, or by using transfer function approach, because it will be easy to understand these filters through transfer function. And we will utilize transfer function to design the active filter with desired characteristics. Okay. So I hope you remember this transfer function is you can say a function of frequency. Here it is a function of S, which is nothing but S equal to j omega. And we are expressing our transfer function hs as the ratio of two polynomials in S. So in numerator we have a2s square plus a1s plus a naught, and in the denominator we have b2s square plus b1s plus b naught. So we have taken here quadratic polynomials in the numerator as well as the denominator. And one important thing here that we should remember is the order of the filter. So in case of active filters, we have a term order. Means we may have first order filter, we may have second order filter, we may have third order filter, we may have fourth order filter. Okay. So the order of the filter is uh, defined by the number of poles that we have in the denominator of the transfer function. I hope you remember that your poles are the roots of the polynomial that we have in the denominator. Okay. So if we have two poles in the denominator, we call that uh, filter as second order filter. If we have single pole in case of your uh, filter, or you can say denominator of transfer function, we call it as first order active filter. Okay. I hope everybody understood this concept, because we have discussed the concept of transfer function in detail earlier. Next. So as I told you, in first order active low pass filter, we will have a single pole appearing in the denominator. And if you look at this expression of transfer function, in case of first order, we will have the term s in the denominator. Okay. And s is equal to nothing but, you can say, j omega. Or so it means in the denominator we will have first order equation in omega. Okay. So in other words, the magnitude of the transfer function will be proportional to, you can say that your transfer function magnitude will be proportional to, inversely proportional to omega, or proportional to 1 by omega. It means as the omega will increase, your magnitude will decrease. Okay. So at all the frequencies above cutoff frequency. Similarly, for the second order active low pass filter, two poles will appear. Two poles means we'll have S square term in the denominator. S square means we will have omega square. So we can say that your transfer function will be inversely proportional to omega square, not omega. Okay, so if we have inversely proportional to omega square means as the omega increases, the magnitude of transfer function will fall more rapidly or more sharply. Okay, so it means as the order of the filter increases, okay, then your magnitude of the transfer function, it decreases rapidly. Magnitude decreases means you can say attenuation, sharp attenuation is taking place. Okay, so that is very very important point here. You should in fact remember this, that by changing the or by increasing the order of the filter, we can have sharp cutoff frequency in case of our active filters. And the concept of order of filter is clear to you. And here we are specifically mentioning low pass filter. Why low pass filter? When we say that it is inversely in case of low pass filter, what happens in case of low pass filter? As the frequency increases or omega increases, okay, your magnitude of the transfer function, it is decreasing. See, it is decreasing. So as the frequency increases, your magnitude of transfer function decreases. That's why we are discussing this thing with respect to low pass filter. Okay, so I hope this thing is clear to each and every student. So now we move to next slide. So now we have talked about active filter in general. We have to look into active filter of various types, that is low pass active filter, high pass active filter, band pass active filter, and band stop active filter. And as we have seen that this is the transfer function which will be defining different types of filters, different types of active filters. So obviously the coefficient of the polynomials of transfer function, these coefficient will decide whether a given active filter will be working as low pass or high pass or band stop. Okay, so we will be adjusting the coefficient of the numerator polynomial. Denominator polynomial is defining the order of the filter, whether it will be first order filter, second order filter, third order filter, which in turn will decide the attenuation characteristics. Okay, whereas the kind of filter, whether it will be allowing low frequencies to pass through, high frequency to pass through, or a band of frequencies, or it will reject certain band of frequencies, that will be decided by the coefficients of the numerator polynomial. So here I'll tell you that which polynomials are to be taken or which polynomials are to be made zero while realizing your particular type of active filter. So first let us see, when we make A1 and A2 zero, means this A1 has been made zero and your A2 has been made zero, we are left with only A naught. So our transfer function becomes like this. So if we get this, we will be able to realize low pass filter. Remember this thing. So we have made A1, A2 0, and this is the transfer function of uh, low pass active filter or active low pass filter. Okay, so right now you can memorize this thing, that okay, when these coefficients will be made zero, we will get low pass filter. So let us check whether our assumption or our values have been correctly defined in the transfer function or not. So obviously in case of low pass filter, what happens, the lower frequencies, these are passed, and the higher frequencies, these are rejected. Okay, so it means the magnitude of the transfer function, it should be maximum at lower frequencies, and it should be zero or it should be less at the high frequency. So if you look at this transfer function, you look at the denominator. If you have zero frequency, for zero frequency we will have constant magnitude of the transfer function. Constant means we will have a constant. Okay, as we increase the frequency, obviously denominator will increase and the overall magnitude of the transfer function will decrease. So for high frequencies, this transfer function will be proportional to a naught by b to s square. So as s increases, hs decreases. So as we move from low frequency to high frequency, your magnitude of the transfer function, it decreases. That means it is allowing low frequencies to pass through and it is rejecting high frequency. It means this transfer function will give us active low pass filter. Okay, I think this was very, very simple and all of you are able to understand this. Now let us move forward. This is what we have for high pass filter. We are looking at high pass filter. You can easily judge this thing by looking at the graph. You can see that as we are increasing the frequency, the magnitude gain is increasing. Okay, it means higher frequencies are passed, they are in the pass band, and the lower frequencies, they are rejected, they are in the stop band. So for that, we have to make a1 and a naught as 0. Means this one, these terms will be removed. So we are left with this one now. So this is the transfer function of active high pass filter. So what will happen for zero frequencies? For zero frequencies, we have s in the numerator. So as your omega tends to 0, your hs will also be 0. It means zero frequency, zero magnitude, means stop band. Now, as we increase the frequency, if we increase the frequency for higher frequencies, we have a naught square and we have b2 square. This we assume insignificant. So for higher frequency, we get this s square will be cancelled and we have a constant value for higher frequency, means those frequencies are passed. So this is how your active high pass filter look like in the form of transfer function. Now, band pass filter. For band pass filter, we have to take A1 and we will take A naught as 0 and we will take A2 as 0. If we do that, then we get active band pass filter. Okay, so here you can say that when we have very low frequency, then it will be 0. When we have very high frequency, then denominator will be very high and again hs will be 0. Okay, so for both very low frequency as well as very high frequency, your hs is 0. It means it will allow to pass through the frequencies within the range. Okay, so you can see here that at very low hs tends to 0. For very high also hs becomes very small. So it allows or it remains constant at a middle frequency range. It means it acts like a band pass filter. Okay, so and then lastly we should look into band stop filter. Okay, so for band stop filter, your a naught will be rejected, sorry, a1 will be rejected and a naught and a2 will have certain value. So this is the transfer function of band stop filter. And the way we have explained the operation of your low pass, high pass and band pass filter, same logic will apply here. And we will be able to see that in case of your band reject filter, your lower frequencies will be passed and your high frequencies will be passed, and in between the range of frequencies these will be rejected. Okay, you can very clearly see here. Okay, so this is how your basics of active filter work in the form of transfer function. So now we try to look at the circuit of active filter. We will look at the circuit of first order low pass filter, first order high pass filter, first order band pass filter, and first order band stop filter. And if we are aware of the concepts of operational amplifier, then it will be very, very easy job to understand the working of these active filters. Okay, so I'll just briefly tell the concept of that operational amplifier to you, and how to use that in circuit, so that we can understand the expressions related to these active filters, whether it is low pass, high pass, band pass, or band stop. So mainly the concept that will be used while analyzing these active filters, the concept of operational amplifier which will be mainly used, that is concept of virtual short. Okay, so if you carefully apply the concept of virtual short, then it will be very easy job for us to understand the working of these active filters. Okay, so let us start with this. So on the left hand side, we have the circuit of first order low pass filter. We have already talked about what is the meaning of first order, second order, third order, fourth order. Okay, so here, since we have introductory portion of active filters in the syllabus, so that's why we will restrict ourselves to first order only. Just for your knowledge sake, I can tell you that we have one R and one C here. So that is the main characteristic of your first order. In case of second order, we will have more than one R and more than one C1. And this way your circuit will scale as you increase the order. Okay, and that was reflected in our transfer function also. Okay, so let us see now first order low pass filter using operational amplifier. So this is our operational amplifier. Fine. You have to identify things separately in a way that uh, in case of your first order low pass filter, if you look at this thing carefully, this is your RC filter. Okay. In fact, this is your RC low pass filter that you already know it's working. This is your RC low pass filter. Okay, and this is our operational amplifier which is working as non-inverting amplifier. Non-inverting amplifier means it will amplify the signal as it is, it will not change its sign. Okay, so this active filter, this active low pass filter is a combination of two things. One is we have RC, this low pass filter, and op amp is doing the job of amplification. If you look at the previous slide carefully, this circuit was also drawn there. Let us see the same circuit is drawn here. We have R and C which is acting as a low pass filter. We have non-inverting amplifier. Okay, and same kind of circuit is drawn here except few resistances are there. This is the one and the same circuit. So I hope now you are able to understand the whole concept, that whatever your RC low pass filter is passing through, that is amplified and then given as the output. Okay, and this is the feedback. We are providing negative feedback in the operational amplifier from the output. So it is showing the feedback from the output to the input. Okay, so this way, if you look at the this circuit in sections, you will be able to appreciate its working. Now let us see. So as I told you, we will be using the concept of virtual short. First, let us understand that concept of virtual short means the voltage across the two terminals, your non-inverting terminal and inverting terminal, that voltage will be same when we have concept of virtual short. So here at this point, we have the voltage VA. See, we have VA. Okay, and at this second point we have the value voltage, say VR1. See why I'm saying VR1, whatever is the voltage across this R1, we are representing it as VR1, and that voltage is going as feedback here. So that's why I'm saying that this VR1. So according to the concept of virtual short, we have to make this voltage VA equal to VR1. That's it. After doing this, now you assume that this op-amp is no longer in the circuit. Just for analysis purpose I am saying, it doesn't mean that op-amp has no role. Okay, just for this, now you can forget about this op-amp, and you look at the other circuit. Okay, so let us see that. So our first job is to find out the value of VR1. Okay, how can we do that? Now you see to this circuit, forget about op-amp. So what we have V naught, and this V naught is getting divided in R2 and R1. Okay, and you now may question that some current may be flowing in this branch. Okay, and but in the case of your virtual short concept, no current flows through these terminals. So that means that in this branch there will be no current flowing through into the operational amplifier. So that way you can here simply visualize this as this circuit. So in this circuit, we have that we are applying voltage V naught, and that V naught voltage is divided among R2 and R1. So means simple voltage divider. So what will be VR1 then? VR1 is by applying voltage division rule. So VR1 will be R1 by R1 plus R2. Okay, into what is the voltage that we are applying? V naught. This is what we have got. Okay, and if you obtain V naught by VR1, this expression you get. Okay, so because of virtual short concept, there cannot be any current in this branch. One thing. Second thing is these two terminal voltages, this will be same. So once you have done that, you can assume that this op-amp is no longer existing. Now we have two resistances in series with V naught getting divided. We obtain value of VR1. Okay, and V naught by VR1 comes out to be this one. So we have obtained VR1. Now our job is to find out VA. Means we have to obtain the voltage across the two terminals. VR1 we have obtained, now we will obtain VA. So this VA, now you look at here. So here what is happening, we are applying V1. This V1 is getting divided in this R and C. Okay, so VA is nothing but the voltage across the capacitor. And capacitor we represent by using Laplace as 1 by Cs. And then we again apply voltage divider. So if you again apply voltage divider, what do we get? This capacitor, that is 1 by C1s divided by R plus 1 by C1s. So again voltage divider, and which voltage is getting divided? V1. This is what we have, V1. And what is the output? VA. This is VA. So we have VA equal to 1 by SRC1 plus 1 into V1. So we have obtained VA and we have obtained VR1 here. And now what we have to do? We have to basically equate the two by using concept of virtual short, that is VA equal to VR1. We substitute, and one more assumption we make that both R1 and R2 are same, are equal. So if you do that, you will get an expression like this. And this is nothing but V naught is what? Output voltage. V1 is what? Input voltage, and equal to 2 by SRC1 plus 1. So ratio of output to input, what is this? This is transfer function. And this transfer function is equal to this. See, in the denominator, what we have? We have first order term for S. Okay, so this is your first order low pass filter. And how it is low pass filter, you can see we have this HS inversely proportional to S. So at low frequency, okay, we will have high magnitude. At high frequency, we will have low magnitude. So it acts like a low pass filter. So it passes your low frequencies and it attenuates high frequency. So this is the working of your first order low pass active filter. I hope each and every student has understood this. So next. So this is your first order high pass filter. So if you look at carefully in this circuit, this is nothing but again the same thing. This is your non-inverting amplifier. And what is this? What we have done, we have interchanged the positions of R and C. And this is nothing but it is your RC high pass filter. So this is your high pass filter and this is your non-inverting amplifier. So same kind of analysis that we discussed in our low pass filter will apply here. So what we have to obtain? We have to obtain VA on the non-inverting terminal. We have to obtain the value of VR1 at the inverting terminal. So the value of VR1 will be same as we obtained in low pass filter. Here you can see that we have already taken R1 and R2 same. Okay. And if we had R1 and R2 both different, we will get this expression V naught by VR1 equal to 1 by R2 plus R1. And when we take R1, R2 same, both equal to R1, what do you get here? We get uh, V naught is equal to 2 VR1. Okay, this R2 by R1 will be 1, 1 plus 1, 2, and V naught equal to 2 VR1. This is what we get here. Okay, and if you look at here, in order to obtain VA, we have input voltage V1. Okay, so we will again apply voltage divider rule, and VA is the voltage across R. So VA equal to R divided by R plus 1 by CS into input voltage V1. We again applied voltage divider and we get VA equal to this one, SRC by SRC plus 1 into V1. And now what we have to do, we have to equate VA equal to VR1 the way we did here. So we have this VA, we have here a VR1. So if you equate the two by assuming R1 equal to R2, this is what do you get. So here again you can see that this is our output voltage, input voltage. This is the transfer function of first order high pass filter. In the denominator we have first order term in S, so that justifies our first order high pass filter here. Okay, you can see here that for low frequency this S will tend to 0 and overall response will be 0. For high frequency it will be constant. Okay, and we will get such kind of response, which is nothing but the response of your high pass filter. Okay, so this is the working of high pass filter with the help of transfer function approach, with the help of you can say mathematical equations, by utilizing the concept of virtual short for operational amplifier. Okay, next. So then we have first order band pass filter. So for band pass filter, if you see carefully, this band pass filter is a combination of low pass filter and high pass filter. See, this is our low pass filter, the same circuit that we saw previously. This is our non-inverting amplifier and this is RC low pass filter. And then this is our high pass filter. So in high pass filter, this is your high pass component and this is again our non-inverting amplifier. So if we cascade the two and we ensure that the cutoff frequency of low pass filter lies here and cutoff frequency for high pass filter, it lies here. Okay, that is your high cutoff frequency for low pass filter and low cutoff frequency for high pass filter. uh, if we ensure that, then we will be able to allow a band of frequencies to pass through, overlapping band. Okay, so and we already know the cutoff frequencies. So if you cascade a low pass filter and high pass filter and ensure the condition for the two cutoff frequencies, we will be able to get the first order band pass filter. Then lastly, we have first order band stop filter. So in case of band stop filter, here we are not cascading the two filters, we are connecting them in parallel. So your low pass filter is in parallel to active high pass filter. See, this is our low pass filter. This is our high pass filter. In fact, they are added together. Okay. So these are in parallel, and both these, they are summed here. Okay. So if we add the two responses, okay, we know that our low pass filter looks like this. Our high pass filter, uh, you can say, it looks like this. Fine. So if we add the two, we will get something of this kind. Okay. Obviously we will need to manipulate the cutoff frequencies accordingly. Okay. So for high pass filter, our cutoff frequency will be high, and for low pass, sorry, for high pass filter, we'll have low frequency cutoff, and for low pass filter we'll have high frequency cutoff. So if you ensure that, then this portion will come under the reject band or the stop band. Fine. So this third operational amplifier, it is acting as a summer. Okay. I hope you know that operational amplifier can also be used to add the two signals as a summer also. So that thing is taking place here. So this is your first order band stop filter. So I hope all of you have understood the concept of active filters. And in the topic of filter, we have talked about firstly the constant K filter or the prototype filter. Then we derived M-derived filter from these prototype filters, and both these were passive filters. And lastly, we have talked about active filters. We have also seen the advantages and disadvantages of each of the filters. We have also seen the designing of these filters. So if we are being given various cutoff frequencies and other parameters, then we can identify, or we can find out the values of various components that are required to design those filters. Okay. So that's all about our topic filter, and I stop here.